It is a common mystery why a tiny iron nail sinks to the bottom of an ocean instantly, while a massive steel ship weighing tens of thousands of tons glides effortlessly across the surface of the water. The answer lies in the fundamental principles of physics, specifically density, water displacement, and Archimedes' principle. Understanding how these elements work together reveals that a ship floating on water is not an accident of nature, but a deliberate masterpiece of mechanical design. To understand why a ship stays afloat, one must first look at the concept of density. Density measures how much mass is packed into a specific volume of space. If an object is denser than water, it plunges straight down. If it is less dense, it remains on the surface. A small piece of solid iron sinks because iron has a density far greater than water. When dropped in liquid, its heavy, compact nature allows it to cut right through water molecules. However, a massive vessel constructed mainly of steel does not consist of solid metal from top to bottom. Instead, the design incorporates a vast hollow structure known as the hull. This broad shape traps enormous amounts of air inside cargo holds, engine rooms, passenger cabins, and empty spaces. Because air is extremely light, the combined average density of the steel shell, cargo, machinery, and air combined becomes significantly lower than the density of the surrounding water. This unique design works hand in hand with water displacement. Whenever any object enters a body of water, it must push aside a portion of that water to make room for itself. As the ship rests in the ocean, its immense size forces a massive quantity of water outward and downward. According to Archimedes' principle, any object wholly or partially submerged in a fluid experiences an upward thrust equal to the weight of the fluid it displaces. This opposing physical dynamic creates two invisible forces locked in a constant battle: the force of gravity pulling the ship downward by its total weight, and the upward force exerted by the water pushing back against the hull. This upward pressure pushing against the bottom of the ship is officially known as the buoyant force. Because the hollow shape of the ship allows it to occupy an enormous volume, the vessel displaces a vast quantity of water before it sits too deep. The weight of this displaced water generates a powerful upward buoyant force. When a ship lowers into the ocean, it settles until the upward buoyant force precisely matches the downward gravitational weight of the entire vessel. Once these two forces achieve perfect balance, equilibrium is reached, and the ship floats steadily without sinking further into the deep. Furthermore, marine engineers design hulls with carefully calculated stability lines and ballast systems. If extra weight or heavy cargo is loaded onto the ship, the vessel simply sinks a little deeper into the water, displacing even more water until the increased buoyant force balances out the new weight. As long as the vessel maintains its hollow structural integrity, prevents water from filling up its internal air chambers, and does not exceed its maximum weight limits, the upward push of buoyancy will always overcome gravity. Thus, through clever structural engineering and immutable physical laws, even the world's largest steel giants easily defy gravity on the open seas.